So the acceleration decreases linearly from to 0 after 30 seconds as the fuel is spent. And the net acceleration while the fuel is burning is given by this funky equation 50 times the quantity 1 minus the fraction t over 30 minus all of that minus 32.174 feet per second squared. And the 32.17 happens to be the acceleration due to gravity. And they want us to find out what is the rocket's maximum vertical height. So, if you know a little bit about the relationships between velocities and accelerations, you've probably learned that or heard of velocity being the derivative of position and acceleration is the derivative of velocity and so we're gonna have to throw some calculus in to that. But let's go ahead and find out how do we get that height or what's going on. So the rocket's going to be accelerating on the way up, and it's going to be reaching some upward velocity. And it's going to keep doing that until the acceleration reaches 0. Now, at some point, that acceleration is going to continue decreasing into the negative values. That means that the acceleration is now in the opposite direction. And what's going to happen is the rocket's going to be slowing down until the velocity is 0. Once the velocity is 0, then it's going to reach a final altitude. Now, from there, we can go ahead and just get the two distances from during those two parts. So we need to find out how much speed the rocket gained, and then we can find out how much distance it covered in that time it was accelerating upwards. And then we can find out, okay, well, how far is it going to travel while it's slowing down to a velocity of 0? Now, the neat thing about this is if you plot the acceleration function, it's nice and linear. They tell you it's linear, and it's symmetric. It should be, because it's, again, linear and starting at some value. So the idea is we can find the time it takes it to reach an acceleration of 0, which ends up being about 10.6956 seconds. So that's the time that the rocket is speeding up on the way up, and then the acceleration is 0. Now, very important, that does not mean that the engines have stopped firing. It turns out the rocket in this question doesn't really quite work in the ideal sense of how we think a rocket should work. The idea is that we think, the moment that a rocket turns off its engines, it was producing a set amount of thrust, and that thrust was always giving it a positive acceleration. But the rocket in this problem is going to be experiencing negative accelerations while the engine is on. So what a lot of people would want to do to solve this problem is they would first want to find out how long does it take for the engines to stop burning, which is not exactly the same thing as when the acceleration is 0 because of the force due to gravity and the other stuff in the problem. Anyways, so just be careful with that. The important thing here to recognize is that the amount of time it spends speeding up is also the amount of time it spends speeding down. So it turns out the total time that the rocket is going up and climbing is twice the time that it takes it to speed up. Because, again, like I mentioned, if it takes it 5 seconds to speed up, then it's going to take another 5 seconds to lose that speed because it's changing at the same rate again, and then come down. So the idea is you take the time, you double it, and then from there, that's going to be your bounds for integration. So now comes the nastiness. We start with the idea that acceleration is the derivative of velocity, so we can thankfully assume this is a continuous function and yada yada yada. Other math things hold, and we can turn this into a fraction and move it over. From there, the idea is that these are tiny little chunks of changes in velocities, and we want to add up all those tiny little changes in chunks. So that's called taking the integral. So the integral of a differential amount of velocity is really just going to be the velocity between two bounds. And so we're going to start from rest, a velocity of 0, to some final velocity. Now when we integrate on the other side, we're integrating the acceleration with respect to time. We're adding up all those little accelerations times from 0 time to some amount of time t. And this is technically bad notation and math, but who cares? We can get away with it here. Anyways, you take the integral of that, and that becomes this expression in your calculator, or you could do it by hand, whatever. You apply your bounds from, which really involves replacing the v with a v1 and a 0 and subtracting them. So v1 minus 0 is v1. Then you do the same thing over here with t and 0, but 0 across all this is 0, so t across all this minus 0 is t across all this. We continue with this beast. Recognizing that the derivative of position is velocity, and all the other math things hold again, we turn that into a fraction. We can integrate the velocity for a function that we got from before, from 0 to 2t this time. And that's going to give us the displacement, or the change in position. So we started at the ground, 0, to some final altitude. And so again, the integral of this is just x, tiny little x's added up, is a whole x between this x and that x. And on the right side, we again apply the integral to the velocity function that we got before, which we got from integrating the acceleration function. So we throw that in here. You again recognize that all of these are polynomial terms with respect to t, so you just apply the polynomial rule. So t becomes t squared over 2, t squared becomes t squared over 3, and you distribute across, and yada, 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 and you do your math, and then now you have your displacement. So this will actually just give you the total answer if you don't break it up into those two chunks, because it turns out, due to the symmetry of the problem, the amount of time spent speeding up is the amount of time spent slowing down. And so therefore, once it slows down, it will no longer climb up. Its velocity will be downward. Okay. So let's say you had just integrated this twice over or once over with from 0 to 30 seconds, because recognizing here that it's going to burn for 30 seconds, you're going to get a negative result for your first integral, which would mean that the velocity change would be negative. It means it lost velocity, or it's moving downwards. So that should tell you, okay, that's not quite right. And if you integrate that expression with respect to time from 0 to 30 seconds, you again would get a displacement or a change in position. And that expression would be equal to some negative number, which would tell you that somehow the change in position was below the starting point. So it doesn't quite make sense if you just do that. And that should give you a hint. Oh, we got to do a little bit more analysis, if you will. Okay? All right. That's a nasty problem. I actually don't expect most people to do this one. This is, if you've got the time kind of thing. 58. Solve for h of the determinant of this expression equals negative 75. So you put this matrix into your calculator, you calculate its determinant. It's going to give you an expression. Thankfully, in this case, it will probably be linear. So you could either solve it by hand or just throw it into the solver. I would just throw it into the solver. 59. 59 is a lot like 56, where we are getting the area. In this case, it is bound between two functions. So if we were to take the area of this sinusoid and subtract the area of this hyperboloid, that would be the area between them. So it's the integral of sine of pi x over 2 minus 2 over x minus 1. And we're going to integrate that from the first intersection to the second intersection. So the first thing you do, solve for the intersections. Then you load in your integral template, load in the functions, lower bound, upper bound, calculate. Okay, 60. A square and an equilateral triangle. They tell us that their areas are equal, and they tell us that the distance from the corner of the square to the apex of the triangle is 67. The important thing is, man, they love to throw these questions in here, is you have to break up the distances. And you got to recognize that we're using Pythagorean theorem. So it's going to be the distance of the square horizontally plus half the side length of the triangle to get us to the apex right here. And then to get the height of our little triangle here that we are working with, you have to take the height of the triangle and subtract the height of the square. Then from there you do the Pythagorean theorem with those two distances. So over here, it's the side of the square plus half of the side of the triangle, and thankfully it's equilateral. And then on the vertical side, it's going to be the height of the triangle minus half the height of the square. The annoying thing is that we have to get all this in relation to one variable so that we can solve it, but we have two unknowns, the side of the square and the side of the equilateral triangle. We need one more equation to relate them, and that's going to be this one up here. It's their areas. With enough experience and calculations, you find out that the area of an equilateral triangle is going to be its side length squared times square root of 3 over 4. And that's going to be equal to the side of the square squared, because their areas are we're told are equal. So we can write a relationship between these to solve for the side of the triangle in terms of the side of the square. And the reason we want to do that is so that when we throw that all into our Pythagorean theorem, we can just solve for x, or the side of the square. All right. Thank you. That's number 60.